Neyman-Pearson's test of acceptance. This presentation is about Neyman-Pearson's test of statistical hypotheses, here called test of acceptance in order to prevent confusion with other theories. Neyman-Pearson's theory was put forward as an improved version of Fisher's test of significance. However, it really is a different approach to testing research data. This test ran as reliably as a jet engine when used for the right purpose. For example, good knowledge and optimal control of important parameters such as effect sizes, type of test, error probabilities, and sample sizes produce reliable decisions as a matter of technical efficiency in the long run. Assessment of the research data comes at the very end, akin to being the spark that sets off the ignition process. Whether the research project itself will produce thrust or a misfire is partly tied up to the earlier parameters, and the output can be understood as a logical deductive product. A guiding example. Imagine that you are in charge of a charity medical center in a remote place. You just received 2 consignments of pills, drugs, and placebo. Unfortunately, labels have peeled off their boxes and you don't know which is which. You cannot wait, so you decide to run a test with 2 small groups of locals. You have placebo pills from earlier deliveries, so you will test one of the consignments against the non-placebo pills. If the effects are about the same or worse, the tested consignment ought to be the placebo. If the effects are greater for the new consignment, then the tested pill ought to be the active drug. So the first step in the procedure is to set the population effect size. This is the known effect of the placebo pill in the population. It had 0 effect on health, yet some people may still show health improvement or ill effects after taking it, of course not due to any active ingredient in the placebo. On the other hand, this is the known health improvement that the active drug has in the population. After taking the drug, people get a large health boost overall. Again, some people may show little effect, even some ill effects, while others may show an extremely large health boost, but overall, about 79% of the population benefit from taking the drug. The 2 populations sit side by side, their main difference being a shift in the health effect they get from the active drug. This is the effect size, a measure of importance. In our case, the effect size is large, standardized as coherence D equals 0.8, which is a mean difference of 0.8 standard deviations between the 2 groups in the population. Good sampling will capture the difference in health effects quite well. However, the sampling distributions will show little overlapping, as they represent errors of estimation, not standard deviation. And this will be a feature that will help us later on to clarify the workings of the test. Now, the second step in the procedure is to select tests for maximum power. Power is a probability of a test of capturing differences due to the alternative hypothesis, in our case effects due to the drug. Thus, you need to think ahead about how you are going to test your research data, and then select the tests that give you maximum power. Among them, parametric tests, which are more powerful than non-parametric tests, and one-tailed testing, which is more powerful than two-tailed testing. Alternatively, you may also redesign your research in order to cater for those more powerful tests. In our case, we are going to use a t-test for independent samples, one-tailed testing, and a sample large enough for ensuring 80% power. Because we have a case where the pills may be either placebo or active drug, we have 2 research hypotheses. Either there is no difference between the groups, thus the tested pills must be the placebo, or the pills increased health as expected, thus they must be the drug. Your research will come down to a decision, therefore. Either one or the other hypothesis explains the research data better. and with it comes the risk of making the wrong decision. The consequences of being wrong are typically higher for one hypothesis than for the other, so the hypothesis that reduces the risk of such consequences should be your main hypothesis. This cutoff here is set to reduce decision errors against the main hypothesis in the long run. So basically, what we have here are the main elements of Neyman-Pearson's test: two explicit hypotheses, a threshold for controlling errors in the long run, and a decision about which hypothesis explains the research data better. In our case, wrongly providing ineffective drugs might bring about worse consequences, for example, preventable deaths, loss of trust, etc., than wrongly providing effective ones, for example, unnecessary treatment. Thus, the placebo hypothesis will be our main hypothesis. Furthermore, we wish to make a small error against the main hypothesis of 1%. The third step in the procedure is setting your main hypothesis. Neyman-Pearson's tests are carried out on the main hypothesis only, while the alternative hypothesis just provides some pieces of information to the test. Let's represent this main hypothesis here now. So the relevant pieces of information are the distribution of the main hypothesis, the probability of only rejecting the main hypothesis in the long run, or type 1 error, which we decided to be 1%. This is the alpha level, which will double as decision threshold later on. And finally, the proportion of the effect size that falls under the main hypothesis. That is, the alpha level also cuts the distribution of potential effect sizes between those accepted under the main hypothesis and those most probable under the alternative hypothesis. Thus, the main hypothesis actually incorporates a proportion of effect sizes, the minimum effect size, which are deemed too small for research interest. The first step will be to set up the alternative hypothesis. And we know that the alternative hypothesis provides two pieces of information. One, the effect size in the population, which is, as we saw, partition between the main hypothesis or minimum effect size and those effect sizes most probable under the alternative hypothesis, and the probability of rejecting the alternative hypothesis wrongly in the long run, or type 2 error, which we can set up at 20%. The fifth step in the procedure will be to calculate the sample size required for good power. Again, power is the probability of the test of capturing results which are more probable under the alternative hypothesis. So we can see that the alternative hypothesis is partition between type 2 error and power at the decision threshold. Therefore, other things being constant, the lower the type 2 error, the larger the power of the research to capture effect sizes under the alternative hypothesis. For Neyman-Pearson, power is best when it is greater than 80%. And finally, calculate the critical value of the test. After setting the parameters about type of test, for example at t-test, one tail, the population effect size, for example at coherence d of 0.8, the level of alpha 1%, the level of beta 20%, and the level of power 80%, and calculating the required sample size for good power, in our case 66 subjects, the critical value of the test can be calculated. It is its location in the appropriate t-distribution, which in our case is a t-distribution with 64 degrees of freedom. This critical value actually has a theoretical probability similar to alpha, that is 1%, in the distribution. Notice also that the critical value stands for all other parameters. In any case, this step can be considered optional, as the critical value and the probability level convey the same information. The seventh step in the procedure is therefore to calculate the test value for the research. Let's say we carried out the research with a recommended total sample size of 66 people, 33 per group, and we obtain a standardized mean difference between those taking the unknown pill and those taking the known placebo of t equal to 2.80. is a probability of 0.003 in favor of the former group. Above test value can be written into following the ways, depending whether you are comparing it against the critical value or you are comparing it against the alpha level. And finally, the 8th step is to decide which hypothesis to accept. Once the test has been set, the results are interpreted deductively, according to where they fall. If they fall beyond the threshold, then you interpret them under the alternative hypothesis. For example, the results suggest the tested pills are the active drug. If, however, they fall below the threshold under the main hypothesis, it will be interpreted under this main hypothesis. For example, the results suggest they are placebo pills. One exception is if they fall under the main hypothesis but power is low, then the study is inconclusive. For example, the results suggest they are placebo pills, but the risk of being wrong is too great as for making this conclusion. In our case, our value falls under the alternative hypothesis, so we can conclude the results are consistent with the drug having a large effect on the population, and therefore the pills must be the drug. And with this, finish the introduction to Neyman-Pearson's test. If you want to know more, this reference about Fisher, Neyman-Pearson's, or null hypothesis significant testing, a tutorial for teaching data testing, will help you on the way as a written document.